Okay, and now we are going to talk about the last distribution. So you all are masters of the z-table, the t-table, the t-test comparison, hypothesis testing. You can answer any of those questions whenever you want. But now we want to tackle our last distribution, which is our chi-square distribution right here. So chi-square distribution is a little bit different from what we've looked at previously. So our chi distribution or our distribution for the z-table and t-table were both symmetric. But as you'll see in just a second, chi-squared has actually a right-skewed curve. So we will actually never be doing a two-sided hypothesis test because this curve is not symmetric. But you could kind of see it looks a little bit more symmetric once you add, as you increase your degrees of freedom nu here. So that's kind of one really key distinction about the chi-squared. So no two-tailed. Two-tailed test. Never, 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 never. So never t alpha over 2 when you're doing a chi-squared test, or not t, chi. But anyways, you get the picture. Never alpha over 2. So the area under the curve is 1, as we kind of see. And again, as our degrees of freedom become large, it does approach a symmetric distribution, resembling some normal distribution. So instead of our t value or our z value, we are going to, experimental or otherwise, we are going to basically calculate a chi-squared value, and chi-squared is often referred to as a goodness of fit test statistic. So we are going to look at the observed values that we measure minus the expected values over here. So that's kind of why it's a goodness of fit test. We kind of know what an expected value basically should be based on, as we're going to see, kind of probabilities and some other kind of parameters. The other unique thing here is this new kind of variable k. So we are going to iterate all the observed values from I equals 1 to k. K is the total number of variables being compared, or what we can kind of say is the number of outcomes. So if I'm flipping a coin, and I could either get heads or I could get tails, k, if I flip the coin 500 times, k does not equal to 500. K is equal to 2. It's the number of outcomes, the number of variables. So it could be either heads or tails. If I'm doing a random number generator from 0 to 9, k is equal to 10 because 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 possible outcomes, 10 possible variables being considered. So your degrees of freedom is k minus 1. Again, I could run 10,000 simulations of random numbers from 0 to 9, but the degrees of freedom will be 10 minus 1 and possibly minus r, where r is the number of fitting parameters. We're going to talk a little bit more about that later. So remember, not the number of samples. People always make this mistake. K is not n, so it's the number of outcomes. And because we have this right skewed, we'll always have basically chi-squared will, and actually you can see here in this expression, chi-squared is always going to be a positive value. So it will always be positive, or the lowest value you can get is basically 0. So when the observed data approaches the expected data of chi-squared, we approach 0. So that's basically what we're going to be kind of doing with the chi-squared. So chi-squared is either you're kind of testing whether coins or kind of some outcomes are true or expected, or we're going to be testing whether basically a curve is either normally distributed or if it fits, like if it's basically a curve, it is a goodness of fit test. So does our data fit some kind of typical type of distribution? And R is going to be the number of fitting parameters. So when we look back and think about our probability distribution X, we had basically 1 over square root pi sigma, and then basically exponential minus x minus mu divided by 2 sigma squared, approximately, again, doesn't matter. But our variable here is x, but we have fitting parameters sigma and mu. So if we're asked if a distribution is normal, or does it approach a normal distribution, or is this normally distributed, our r is equal to 2 because we have 2 fitting parameters, sigma and mu. So next time we're going to do several examples, and I think that's the best way to illustrate this concept, but more on that next time. All right, have a good one. See you later. Bye.